Lesson 5-6. The most general applications of Bernoulli's equation. The previous examples in the last lesson of Bernoulli's equation had simplified conditions. But Bernoulli's equation works in the real world. Let's say water circulates throughout a house in a hot water heating system. If the water is pumped at a speed of 0.5 meters per second through a 4-centimeter diameter pipe in the basement under a pressure of 3 atms, what will be the flow speed and pressure in a 2.6 centimeter diameter pipe on the second floor 5 meters above? Assume the pipes do not divide into branches. So we have one pipe. So we have our pipe down here at the bottom, and then that goes up top, and it narrows. So at the bottom, we know that we have a speed of 0.5 meters per second, and our diameter is 4 centimeters, so our radius is 2 centimeters. And our pressure is 3 atms. So up at the top, I want to know the speed, and I want to know the pressure, and I know my radius is 1.3 centimeters. And I know the height is 5 meters. So the height at the bottom let's call 0 meters. Well, to start off by finding the speed, let's use the equation of continuity, because I know the area and speed in the basement, so I can find the area and speed in the top. So our area is pi times the radius, should be in meters, squared. That's the area, and then the speed at the bottom was 0.5 meters per second. At the top, our area is pi, its radius, squared times its speed. So divide, and you get the speed at the top is 1.183 meters per second. All right, now to find the pressure, we use Bernoulli's equation. P plus 1/2 rho v squared plus rho g h equals P plus 1/2 rho v squared plus rho g h. So our pressure at the bottom is 3 atmospheres, so it would be 3 times 1.013 times 10 to the 5th pascals. That's 3 times an atmosphere, plus the 1/2, it's fresh water, so it's 1,000 kilograms per meter cubed for the density. And the basement, the speed is 1/2 meter per second. That's squared. The density for the rho GH is 1,000. G is 9.8. And the height is 0. At the top, we're looking for the pressure. The density is still 1,000. And the speed is 1.183. And the density is 1,000. G is 9.8. And our height is 5 meters. All right, run all that through your calculator. You get 3.03125 pascals equals our pressure on the other side plus 4.9700 pascals. So subtract, and your pressure is 253.425. Divide that by 1.013 times 10 to the 5th pascals to get ATMs, and it comes out to be 2.5 ATMs. Here's another application. The tank is open to the atmosphere on the top. Find an expression for the speed of the liquid leaving the pipe at the bottom. All right, so we have movement and all that stuff, so we can use Bernoulli's equation. So P plus 1/2 rho V squared plus rho GH equals P plus 1/2 rho V squared plus rho GH. So let's let the left side be at the bottom. So here, where the water's exiting the little pipe there, the pressure is 1 atmosphere. Has some speed, but 0 height. So all that 0. At the top, it's open to the air, so at the very top up here at point 2, the pressure is 1 atmosphere. And it's not really moving, so that part's 0. We have rho GH. If I subtract 1 atmosphere from both sides, they'll cancel out. And that's all I'm left with. Divide by the rho. Multiply by 2. And square root. So our speed would be the square root of 2GH. So it should come out the same speed no matter the density of the fluid. How interesting. How do I know that? Because density is not part of my equation. What if we added a little bend on that so that the water was shooting straight up? Because Bernoulli's equation is conservation of energy, the water would rise up to the same height as the water in the tank. So, here's the quick reason why. So the pressure both inside the tank and out here, where it's at its highest point, is 1 atm, so they cancel out. Inside the tank, it's not moving, so the speed is 0. At the highest point, the water has to stop before it comes back down, so that's 0. So I have rho GH equals rho GH. So the densities are the same, G is the same, must mean H is the same, be the same height. An air dancer is used to draw attention at used car lots. The behavior is explained by Bernoulli's principle. Initially, the moving air, which behaves like an incompressible flow in the open-ended air dancer, creates enough pressure to inflate the tube. As the tube stands more upright, the turbulent air inside flows more freely, and its speed increases. But it decreases the pressure and no longer support the mass of the little nylon figure. And so the material collapses and creates a kink. That constriction causes the air speed to temporarily slow and the pressure to rise. And since the pressure rises, it stands up again, but then the speed increases and the pressure decreases and it collapses again. If we have power in a fluid flow, power is the rate of work or energy. Bernoulli's equation terms are in energy per volume. So if I multiply Bernoulli's equation by volume and divide by time, that's flow rate. So power is simply Bernoulli's equation multiplied by the flow rate. I'm sure you can work that out in your problems. So apply yourselves to these applications. Have a good day.